Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper from the Hugging Face trending list, published on July 24, 2025, about 5 days ago. This paper tackles quantization, the process of shrinking huge LLMs to run on smaller hardware. It shows that a popular method, GPTQ, is mathematically identical to a classic algorithm from a totally different field. The paper is titled The Geometry of LLM Quantization, GPTQ, as Babai's nearest plane algorithm, and this is a big deal. This discovery finally gives the method a solid theoretical foundation with a clear geometric meaning and a formal guarantee on its accuracy. So, how do they actually prove this surprising connection? This table lays it out side by side. On the left, we see the steps for the GPTQ algorithm, and on the right, the steps for Babai's nearest plane algorithm. The authors show that quantization is essentially a closest vector problem, which is the classic task of finding the closest point in a grid-like structure, called a lattice, to some other point. Here, that lattice is defined by the Hessian matrix of the layer's inputs. When you run GPTQ in reverse, its steps become mathematically identical to Babai's algorithm. Building on that, this figure gives us a fantastic visual for what's actually happening. The top row shows Babai's algorithm at work. The black dots form the lattice, that grid of possible quantized values we mentioned. The green cross is our original high-precision value. The algorithm then takes these projection steps, essentially walking along specific directions until it lands on the closest lattice point. This is the geometric process that GPTQ is secretly performing. The bottom row contrasts this with other methods, showing how different algorithms carve up the space into different rounding regions. So knowing that GPTQ is this geometric walk, a key question arises. Does the order of the steps matter? Well, it turns out it matters a lot. This table presents a new method the authors propose, called min-pivot, shown as algorithm 4 on the right. It's a clever strategy for finding the best quantization order. It analyzes the Hessian matrix, which, again, captures how sensitive the model's output is to its weights, and it strategically reorders the process to minimize the error that builds up. This simple change helps make the final compressed model more accurate. And to really cement the equivalence between these two algorithms, the authors provide the mathematical proof you see here. Now, this chain of equations is pretty dense, but what it's demonstrating is crucial. It proves that once you perform the projection step from Babai's algorithm, that geometric walk we saw earlier, any further error propagation steps from the original GPTQ method are actually redundant. They don't change the outcome. This formal proof confirms just how deep the connection runs, showing the two processes are not just similar, but mathematically identical in this context. So in conclusion, this work beautifully bridges two different fields. It reveals that GPTQ has a deep geometric meaning and a solid theoretical backing. This insight opens the door to using decades of progress in lattice theory to help us build even better quantization algorithms for the future. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.